So here we are in Moodle, and here we can see the range of topics we've covered since we began, ending here. And so what you'll see is that there's two sections. There's the capacitance resistance, simple circuits, Kirchhoff's laws, so the kind of circuits section that we've been doing over the past 4 weeks. And then there's the properties of electric charge, electric field, electric flux, and electric potential that we did over the first 4 weeks, and then Millikan's oil drop experiment, which was sort of a good application of these concepts. So you want to review the early concepts and make sure that you're able to do circuits. And the other thing that exam questions will be like quiz questions, except for a couple things, except for one thing, and that's that I'm likely to ask you one to three essay questions. And the essay questions could be explain the properties of electric fields and how we represent them, or explain the concepts of electric field, or explain the concept of electric flux and Gauss's law, or explain the difference between electric potential and electric potential energy. So you definitely want to review those concepts of electric force, electric field, electric flux, and electric potential, and the ways in which they're related. Amongst the circuits problems, the two kinds of circuits that we haven't done are a Kirchhoff law circuit, where there are two power supplies or two batteries in the circuit, and you need to use those rules, the Kirchhoff's current rule and the Kirchhoff's voltage law, to solve the problem, and then RC circuits. So you definitely want, as much as possible, to have completed assignment 8B and the lab and watched those videos. There will definitely be questions, at least one or maybe two questions on the quiz on that topic. And in order to do this, you do have to understand simple circuits and Ohm's law, of course. And then as far as the earlier part goes, there could be calculation problems similar to what we had in quizzes and labs, and as I mentioned, 1 to 3 essay questions on concepts and explaining things. So I think the circuits are a little bit easier. Let's go back and review force, field, flux, and electric potential. So in week 1 we learned about Coulomb's law and how to find the force between 2 point charges. And that's pretty straightforward. They have to be point charges, and the force depends on the 2 charges and the distance between them squared, and the K is just a shorthand way of writing 1 over 4 pi epsilon naught, and the value for that is given on your equation sheet. From here we moved on to the concept of electric field. And so if we have a point charge and we place another point charge here, it has a force on it, but they're not touching, so why does it have a force on it? So the explanation is that the original point charge has an electric field which goes out in all directions and gets weaker as it goes out. And so when we put a second charge here, it has a force on it which is proportional to the charge that we put there and the field strength at that point. And so the electric field is defined as the force that we get at any point in space divided by the charge we put there. So if we go to the same point and we put a charge that's twice as big, the force will be twice as big, but when we divide the force that's double by the charge that's double, we end up getting the same value, and that value will have units of newtons per coulomb. So that's the concept of electric field, and it's related to the more general concept that we discussed about field in general, where field is the values throughout space of any quantity. So if I ask you to explain field in general, you will mention that there are scalar fields, like a temperature field or a pressure field, and there are vector fields, like a wind velocity field, or in this case, an electric field. So values throughout space of any quantity is what we call field in general. And the electric field is the force per unit charge at any point in space. And so when we use Coulomb's law, we find out that if the force is kq1 q2 over r squared, and we divide by that second charge q2, we end up with the equation so we can calculate the value of the electric field using the value of the charge that we're finding the field for divided by the distance from the charge to the point. And when we calculate our electric field, remember there's no charge there. We're just going to this point and we're using this equation. Or we're going to this point, now the r is different. Or if we go to this point, now the r is different. And if we have more than one charge, then the electric field at any point will be due to the electric field due to this charge. Positive charge, the field goes away from the charge. A negative charge, the field goes toward the charge. And if we call this Q1 and Q2, then Q1 has an electric field vector in this direction, and Q2 has an electric field vector in this direction. And we add those two vectors to get the resultant vector. The resultant vector would be the vector sum of those two vectors. And so the total electric field at this point is the sum of those two electric fields. And so by drawing electric field lines, we can give a picture, a visualization of what the field might look like throughout space due to one, two, or more charges. And there are rules for electric field lines, and you should go over those rules. The rules are that the number of field lines are proportional to the charge, and field lines always start on positive charges and end on negative charges. And the direction of the field at any point is tangent to the field line at that point. And electric field lines never cross, and the density of lines is proportional to the field strength, so where the lines are more spread out, the field is weaker. All of that. And once we understand field, then we come to the idea of flux. So if I take a surface element and I put it in a field, let's say this is a circle, then field lines go through the circle, they pass onto the surface and out of the other side. And if this were a sphere, like supposing this were an egg or something three-dimensional, then the field lines go in and go out. And you can see that wherever I draw a closed surface that doesn't enclose a charge, the number of field lines that enter and leave that surface are equal. And so that leads to the relationship of Gauss's law. So we have the definition of electric flux and Gauss's law. I'm going to write those down. Excuse my crappy writing, but the general definition of electric flux is the double integral of the dot product of E of two vectors E dot dA. In a simple sense, that's the value of E times the value of A times the cosine of the angle between them if the surface is flat. And so in most cases where we're dealing with simple situations and flat surfaces, we use EA cosine theta. Visually, conceptually, it's the number of field lines that pass onto a surface or through a surface. So these two, this is the definition of electric flux, this is the simplified equation for electric flux, and this is what we were talking about. It's the relationship between electric flux and any closed surface. And so if we go back to these three surfaces, and we think of them as three-dimensional surfaces, every field line that goes in comes out because there's no charge enclosed. Whereas if we draw a closed surface, if we take a sphere and we use it to enclose the charge, then 8 field lines go out and no field lines go in. And if I were to draw a closed surface that only included half of the charge, you'll see that, and the drawing's a little confusing, but you can see that 4 field lines go out of that surface I draw because it only encloses half of the charge. And so that's Gauss's law. These are all explained in more detail in the videos. I don't want this video to go on too long, but I do often ask to explain the concept of electric flux and explain Gauss's law. And it's important, if you're explaining the concept of electric flux, you use the definition and you do some description like I just did. And Gauss's law is not the definition of electric flux, it's the relationship between electric flux through a closed surface and the charge inside the surface. And of course I didn't mention it, if you enclose a negative charge, then 8 field lines go in. So if you saw 2 black boxes, and just think of these 2 black boxes as separate and far away from each other, and you looked at this black box and this is what you saw. If you could see the electric field, what would you see? You'd see 4 field lines coming out, so you know, oh, there's a positive charge, a net positive charge, right? And if you see this, what do you see? You see field lines going in, so there's a net negative charge. And what else do you notice? You notice there's twice as many field lines, so there's twice as much charge. So what might there be in this box? There's a net charge of a net positive charge, and you don't necessarily know the detail. There could be, this could contain 4 positive charges and 2 negative charges, which gives you a net charge of 2. And then this could be 6 negative charges plus 2 positive charges, which would give you a net charge of -4, so there's twice as many field lines. So by seeing the field lines going in and out of a box, a black box, you can tell what's in there. That is using Gauss's law. So just like finally talking about electric potential energy, it's related to the concept of force. Force is measured in newtons, and if we have a single charge, it has a field which is measured in newtons per coulomb, and it's the force per unit charge at any point in space, and we calculate it this way. Similarly, if you have a single charge, you don't have any energy, but if you have another charge, you have energy, right? Because if I put these 2 charges together and hold the first charge down and let the second charge go, the second charge is going to have a force, it's going to accelerate. It's kind of like the electric field is a compressed spring, and this charge goes off, losing electric potential energy and gaining kinetic energy. And so here we move into the realm of energy. And so the electric potential energy due to any 2-point charges is given by this equation. But if we take the charge away, this charge still has an energy field. right? So when we put the charge here, it's in its energy field, and that energy field is what we call electric potential, and it has units of volts. It has units of joules per coulomb, which is a volt. So that's our concept of volt. And for point charges, we can calculate it simply like this. And notice these two equations look very much alike, but one is r squared and one is just r. And if you have a system of point charges, then you use this. The other important difference is electric field is a vector and potential is a scalar. So if we look at a simple example, 2 point charges, and we want to calculate the electric field at the center, then the field due to the charge on the left goes away, and the field due to the charge on the right goes together, and those two vectors add. And so the electric field has a value which is the sum of those two vectors. Whereas if we want to calculate the electric potential at the center, you're going to have K Q1 over R1. The R1 would be that, the Q1 would be that, plus K Q2 over R2. So the distance is the same because it's the midpoint. The K is the same. The charge has the same magnitude, but it's negative. So these two are going to sum to 0. So although the electric field at this point is not 0, the electric potential at the center is 0. Now if you move to a point over here, the negative potential is going to be bigger than the positive potential, and it will be a net negative electric potential. So anyway, you might want to go back and review those concepts and be aware of which equations you need to use for which kinds of problems. So review circuits, review force, field, flux, and potential, and look through the quizzes and the assignment. I said lab last time, but it's assignment questions that are important. And so you might go back and do some of those multiple choice questions, just refreshing your memory of all those earlier concepts that we haven't used in a while.